Alright, so I'm going to show you a nice shortcut using Newton's first law to solve a problem. First I'm going to solve it using Newton's second and third, and it gets a little convoluted, so I'll try and write small. Bear with me. If you don't really want to hassle with this, you can just fast forward to where it changes to solving by Newton's first law. Alright, anyway, maybe just kind of go through the steps real quick. So this is the one with the sled, Joe down on the sled, pulling on the baby seal. Okay, the seal weighs a lot less than the sled, so the seal is going to come a lot further than the sled. The question is, how far will the seal move? And so here's the setup. We have, I got to write this kind of small. Here's the seal, and it's got its, I'll call it body A. So MAG and N. Now the subscript on the normal force should be whatever the substance is it's sitting on, or sitting on it. In this case it's the ice. And then over here we have, and they're connected up, but over here we have the sled, and that's got a much bigger, I don't have much room, so I'll just make it a little bit bigger, but it's really, this is 360 kilograms if you look at your problem versus 40 kilograms over here. And that's going to have an equal and opposite normal force, and that's also from the ice. And then they're both being pulled together, and so the force, here's where Newton's third law comes in. Now I realize that this is equal to that, that's equal to that, but that's not, those aren't examples of Newton's third law because it's only one body. Okay, you have to have two bodies for Newton's third law. So this then is equal to this force. Now I'm going to put a 3 thing there to show that those are also congruent. So that's the only part that's Newton's third law, but we're going to call this is a certain kind of force called a tension. It's a type of, it fits into a category of forces called tensile forces. And tensile forces involve ropes or cables. A rope, you cannot push somebody around with a rope. So a rope only pulls, so tensile forces only pull on things. That's one thing about them. The other thing about them is, see, the rope connects the whole thing. But notice how they're both pointing towards each other, like in a tug of war. Tensile forces have that kind of, they both face each other, the force on either side on a tight rope. Okay, so this is the force of, now this is really the force of body B on A, body B being the sled, and this is the force of body A on B. Okay, so there's a nice free body. Now we also want to add something to this, and we'll add this in a different color because we're really only supposed to show forces on a free body. But we also know that between these two, it is 15 meters. That's given. And we realize that the you can put this in there, that MA is equal to 40, MB is equal to 360, and this one's going to go. This guy's going, the seal is going to go a certain distance x, and that's supposed to be straight, and then the sled will go 15 minus x, a little algebra trick there. Okay, so we know that much. Now let's go to Newton's, second law. And so from Newton's second, now I'm sorry, I got to write kind of small. We have, otherwise I'm going to go to a whole other screen. We have F equals ma, so in the x direction on the seal we have T of B on A equals the mass of A, and then for Joe and the sled we have T of A on B equals the mass of B times acceleration of B. Now, I haven't connected them up yet. Those are just two separate free bodies. Now, once you connect them, you have to establish the pecking order, or establish which way is positive, which way is negative. Let's make the assumption then that anything, back on our figure, that anything going in this direction is positive. Okay? So now we connect these two up from Newton's third law. So different color here. All right. Hope you can see this. From Newton's third, we have, it's not, I hope you can see that, that is every force has an equal and opposite force of body A and force of body B, equal and opposite reaction force. So we have T of B on A equals the opposite of T of A on B. Okay, that's from Newton's third law. Now I can take these and put these together and do a little algebra here. So let's come down here. Those connected those two up. I mean, it's kind of cool to see how it all works. And sometimes you have to do it this way. But I'll show you a shortcut in a little bit. You can avoid all this work. So now let's go to, back to red here. Now let's go to add these two up. Well, in that case, I'm going to put these two together, substitute in, and so I have MA A equals the opposite of MB AB. Okay? So I'm avoiding putting numbers in as long as possible. So I want to really find, if I can find the acceleration of that seal and how long it slid, that kind of thing, then I can figure out through orange mirror how far it slid. Okay, so the acceleration of the seal then is equal to the opposite of MB over times AB over MA. Now, I know the ratio here because this was 360 kilograms, this was 40 kilograms, so 360 divided by 40 is 9, and so this is equal to, with numbers, negative 9 AB. So I have this relationship. Acceleration at A is equal to negative 9 AB. Okay. Now table that for a minute. I'm trying to find out what is the difference in X. So let me go to orange mirror. All this is still trying to solve the same problem. So in orange mirror, second orange mirror, I have, for the seal, I have X, which is really delta X. I'm not going to leave the delta there, but it's X. That's how far the seal moves. And we're establishing that this is positive displacement. So the seal is moving in the X direction. And that equals, now V naught X is 0. So that goes away. It equals 1/2 A sub, and for the seal, we're looking at A, times T squared. Now, for Joe, this is kind of a tricky part. Joe and the sled are moving that way, and they move a distance 15 minus X, but direction's important here. It's displacement we're talking about, not distance. And so it's going to move negative 15 minus X. And that equals, no V naught, 1/2 A sub B. Now, the T, the time that the seal moves, is the same time the sled moves, right? We're going to move this for the same amount of time, so that's T squared as well. Well, right now, it looks like we have two equations and three unknowns. We don't know X, we don't know A, and we don't know T. But we do know some things. So I can go ahead, I know like how the acceleration of A matches up the acceleration of B. I know the relationship between those two. Actually, right now, it's 1, 2, 3, 4 unknowns. So I'm going to do a couple of things. I can do a substitution. I can take this and substitute that in for that, okay? And then I can divide, there's an old trick here, as long as you're not dividing by 0, you can divide this by this and this by this. That's legal, to divide both. The old algebra trick. Good for the ACT sometimes, on those really hard problems. So I divide this by this. So I end up with, once I do that, my halves will cancel, my T's are the same, so they'll cancel, and then I'll have my new substitution, and my A, B's, when I substitute that in, my AB over AB, that'll cancel. And I'm left with this fairly simple equation. X over, I'm just going to switch this if you don't mind, X minus 15, yes, it's the opposite of, equals negative 9. That's it. Everything else canceled. Right? Okay? You can prove it to yourself if you want to. Now when I go ahead and do the multiplication, I'm going to now get, I'm trying to solve for X. So this is X then equals negative 9 times X minus 15. So therefore, I bring this distribute the -9, I got x equals -9x, right? I'm going to bring that over here. That gives me 10x equals, and then 9 times 15 is 135. Therefore, x equals 13. X equals 13.5 meters. Now, I just solved this with all these. I had to go to all these different steps, go through all these different laws, Newton's second law, Newton's third law, back to Newton's second law, over to orange mirror kinematics, do some manipulation, some fancy algebra, and finally came up with 13.5 meters. Probably would have taken 15 minutes, right? At least 20 minutes maybe, because you had the daggone free body diagram, all that stuff. Now, let me show you a brilliant shortcut, which, I can't take credit for this one. Constantine from Russia many years ago, a student of mine, kind of turned me on to this idea, this way of approaching things, sometimes through Newton's first law. And it's a much, the way I did it was a blunt instrument, but this is a much smarter way. And so here we go. Now we're going to solve, solve same problem using Newton's first law shortcut. So we talked about this, and this was sort of introduced last week when we did the, I hope it's last week, depending on what year you're seeing this, but earlier, when we did the cart with the steel balls rolling down the cart, and we said while those steel balls were on the cart, that's essentially one body. And the reason why the cart moves is to keep the center of mass relative to the table in the same position. So we can do the same thing here. Here's my seal, here's my sled, and if I draw a dotted line, that's kind of a nice thing to do. You want to establish your system by drawing a dotted line around it. I'm saying that's my system and that's the body. There's one body here. Okay? One body, no external forces. I want to know, basically what it says is, unless there's some kind of unbalanced external force, which in this case there's not, there's no wind blowing on them, there's nothing else pushing on both of them, so therefore there's no unbalanced force, and therefore Newton's first law says a body at rest will stay at rest. Which means this whole thing's my body, its center of mass, and I should say that really, Newton's first law should say a body's center of mass stays at rest. That make more sense. I'm going to change that. But anyway, a body's center of mass, or a system of bodies, centers of mass, stay the same, the whole thing stays the same place. So I put a little, I'm assuming this being more massive than this, I put where I think the center of mass is somewhere in here. Now it's like a teeter-totter. If I have, or a stick here, if I bring my fingers in, they're always going to touch at the 50 centimeter mark. Unless I put a weight on one side, if I add like the dreaded copper paper dice, when I add those, now my balance point on my fulcrum, okay, we'll study fulcrums and torques. Great. All right. Duct tape. But now this thing, I know where it's going to meet already, so I've already messed with this. So it's going to meet at right at about, this thing turned around, about 56, I believe, or around 56 and a half. So there's my new balance point. See, so if I put a 2-pound weight over there, my balance points will be almost right next to it. So it's sort of the same idea. It's like you put the seal and you put the sled on a teeter-totter, and then where would I have to put the center of that teeter-totter, the fulcrum, to make the whole thing balance? That's really all we're doing. So there's a formula that goes with this to find centers of mass, and it's right here. This is my CM. Okay, so here's your new formula. You can do it in the X, you can do it in the Y, you can do it in the Z. We'll do it in the X, because that's all we're going to care about right now. X center of mass, it's capital C, capital M. Don't think it's centimeters, it's not. It's capital C, capital M. X center of mass is, I'll show you the long version first, X1 M1 plus X2 M2 plus X3 M3 plus ... keeps going, all the particles. We only have 2, you might have 10, divided by the entire mass, That, when you plug into that formula, that's your center of mass. That's where your center of mass is from wherever you pick a convenient location, wherever you pick the origin. Now, a shortcut way of writing this, in case you're interested, the pocket version, x center of mass then is summation of from I to infinity. You can have an infinite number of particles here. Would be xi mi all over the entire mass of a whole system put together. So we could use this to find the center of the mass of the solar system. You know, and now it's obviously going to be where the sun is, and not right at the center of the sun though. It's going to be depending on where Jupiter, it changes some. Where Jupiter, where Uranus is, all those, where Saturn is, where the Earth is. So it depends. But it could be a center of mass of anything you want. You can use this. Now, in AP physics, or when you take calculus, this will turn into an integral and it'll become an extended object, and that's when it gets really difficult. I think that happens at the end of chapter 9 in AP, and from then on, the class takes a whole other level. Okay, but don't worry about that. Here we're going to keep it in this class simple. We'll keep it as particles. So 2 or 3 at the most. Well, here we go. We're trying to find the center of mass between the seal and the sled, and that'll tell me how far the seal moves. So I'm going to go ahead. Now I need to establish a origin, a point, and that could be anywhere you want. Usually make it somewhere convenient. So I'm going to make, here's my line of motion, and I'm going to make the origin right there at the seal. Okay, so here's my x-axis. Here's my y-axis, but it doesn't make any difference. The y-axis, this thing's not moving. Now, sometimes you do have x and a y. We might touch on that this year, but that's more of an AP physics thing as well. Okay, so to figure out where the center mass is between these two, I go ahead and take x, this is plugging in my formula, x center of mass. Now, this, I'm not using the x3 and on, because I only care about a seal and a sled. So I'm going to say for the seal, see this, I put the origin right there where the seal is. So the seal's distance from the origin is 0. So for the seal, I say 0 times 40 kilograms plus, now x2 is the distance that the sled is from the origin, and that's 15 meters times its mass, which is 360 kilograms, and divide the whole thing by the whole mass, which is 400 kilograms. Now, when you do the math here, you got some 5,400, some big number there, and then you divide it, that goes to 0. You divide that by 400, and voila, you get the answer. The seal will move 13.5 meters. So you compare this to that. Would you rather do that on a problem, or would you rather do that on a problem? Now, all this requires is that you memorize, I'm not going to give it to you on the next quiz, you memorize that formula. Okay? Depending what year it is, this is 2009, so they have a quiz coming up. But if you're 2015, we're flying around in spaceships, then it may not be a quiz coming up. But anyway, so I try and keep this generic. So voila, there's the magic. Excuse me.